Pre-calculus students, welcome to your 9.7 notes. We're going to look at probability today, continuing our counting principles and taking it to the next level. So let's get going here. First of all, some terminology. You guys can read it. I'm not going to read it all to you, but experiment, outcomes, sample space, and event. You'll need to know what those four terms mean. I'll try to show you when we get to those where we run into them. So let's start with sample space. Find the sample space for each of the following. One coin is tossed. So the sample space is not just saying, well, there are two possibilities, but it's actually going a step further and saying, well, exactly what are those possibilities? It could be tails or heads. I'll just use T and H to abbreviate that, and it would look like that. Now, when we go to two coins, our sample space gets a little bit larger because we have some different possibilities. We could do heads and heads. We could do heads and tails. And we're actually considering order when we do this, so tails, heads would be different than heads and tails, and then finally tails and tails would be our fourth option. Okay, so we use sample space to calculate probabilities. This whole situation of heads, tails versus tails, heads, we'll talk about that later. You could look at it experimentally. Okay, one die is tossed, so that, assuming it's a six-sided situation, we'd have 1 through 6 is our possibilities, like that. And then we have one coin and one die, so I would look at it this way. We could go heads and 1 through heads and 6, so we're going to have 6 possibilities with heads, and we'd have the same 6 possibilities with tails, just T instead of H. And now you can see the list of 12 for the sample space for a coin and one die. Alright, so let's take a look. Probability. If an event E has N of E equally likely outcomes and its sample space has N of S equally likely outcomes, the probability is N of E over N of S, or just simply the desired versus the total probable. That's always going to be between 0 and 1. 0 would be something that can't happen. 1 would be something that is certain. We can also convert that decimal to a fraction or a percentage if we so choose. So let's take a look at an example of probability. My favorite basketball player of all time, Shaquille O'Neal, was a 50% free throw shooter after being fouled while attempting a 3. That's a funny scenario. What is the probability that he makes all 3 free throws? So the way we're going to look at it, we're going to have to do multiplying, or I'm going to treat this as a sample space problem to begin with, actually. So let's look at the possibilities. The possibilities, since he's a 50% free throw shooter, a make is as likely as a miss. So I'm going to use plus to represent a make and minus to represent a miss. So I'm going to go through and list all the possibilities. So we could do 3 makes, we could do 2 makes, then a miss. We could do 1 make, then a miss, then a make, or we could do a make, then 2 misses, and then I'm going to go to where he starts with a miss, and so on. Our sample space would look like this. These are all the possibilities. Again, the key being here, 50% free throw shooter, so a make is just as likely as a miss. So we consider this sample space. The only one that includes him making all 3 would be this option right here. So it's 1 out of 8. Now some of you may say, well, we could just do some multiplication. The first event times the second times the third would be 1/2 times 1/2 times 1/2, or just simply 1/8, and that would be a legitimate way to handle this problem as well. Probably the more challenging question would be, what's the probability that he would make 2 out of 3 free throws? And so then you'd have to look through and find the different options that include 2 makes, or we could ask if he makes 1. It would be, again, a little bit more challenging question. A card is drawn from a standard deck of cards. What is the probability that a jack is randomly drawn? Folks, if you're not real familiar with the deck of cards, you'll want to look that up. Just Google it. I'm sure you can find it. But essentially the idea is we have 4 jacks, 1 from each suit. There are a total of 52 cards. That gives us a fraction of 1/13. All right, two dice are tossed. What is the probability that the sum of the two dice is 7? So let's look at the two sample spaces. This is our desired outcome. We could do 1 and 6. We could do 2 and 5. We could do 3 and 4. And then we could also reverse these: 4 and 3, 5 and 2, 6 and 1. It's important you consider order on a problem like this, where your total sample space, you've got two dice, each has 6 numbers, so your total sample space is actually 36, and we have 6 options here that would satisfy what we're looking for. That's our desired outcome. 6 out of 36, or just simply 1/6. There are shorter ways that you could approach that problem, but I think that's a decent way to look at it. If you get a sum that was less than 7, something like a sum of 5, that might create a more challenging problem there, because there's, like I said, some of those backdoor approaches that look a little bit simpler might be more conducive to what you want to do on that problem. Now, number 5, I probably should have rewritten this question. It's basically the same thing you just saw on number 4. So again, our solution here is 1/6. All we're doing is, instead of 6-sided die, we have 12-sided, but it's just the numbers 1 through 6 appearing twice. It doesn't change the question or the problem or the solution. All right, so here we go. Some ACT scores. What's the probability that a randomly chosen student from the group scored at least 28? So what I've done here is I have totaled the number of students that scored anywhere from the 3 groups of 28 through 36. These 3 numbers here gives us 164 students that scored at least 28. And then the total number of students would be our sample space. If you add all those numbers together, you get 966, which gives us a decimal approximation of about 0.17. Now, if you preferred to change that into a simplified fraction, that's fine. If you like the percentage better, that's also fine. But I'm just going to leave it as a decimal. Two events are mutually exclusive if they have no common outcomes. For example, rolling 2 dice and getting a sum of 6 or a sum of 9 are mutually exclusive events. One doesn't have to happen for the other, and they're not really connected. They're completely different things. Now, when we talk about probability of the union of 2 events, we're talking about if A and B are events in the same sample space, the probability of A or B occurring is given by the union of the 2 events, which would mean the probability of A plus the probability of B minus the intersection of A and B. So we'll talk about that in just a moment, why we have to do that. If the 2 events are mutually exclusive, in other words, there is no intersection, no repetitive data, then we wouldn't have to worry about subtracting. So that's what you see here. All right, a card is randomly selected from a standard deck. What is the probability that the card is either a jack or a heart? So we'll take this one at a time. As we've talked about before, we know there are exactly 4 jacks in the deck of cards. We also know that there are 13 hearts out of the 52. The one thing we have to do is consider, though, in these 2 sets, I'm counting the jack of hearts, that single card, I'm counting it twice. So I have to go back and actually subtract 1/52. The jack of hearts still counts. It's still part of the desired outcome here, but it only counts once. We can't count it twice just because jack and heart each show. On part B, it says, what's the probability that a card is an even number, non-face card? This one's actually a little bit simpler problem. We just have to consider that each of the 4 has 5 even numbers: 2, 4, 6, 8, and 10. That gives us a total of 20 cards out of the 52, so 20 52nds, which we would simplify to 5/13. All right, we're going to work through this next one pretty quickly. It's a pretty straightforward problem. It's just a different way to present data. Use the diagram at the right to find the probability of staying at home over the break. So the stay at home group represents exactly 21% of the data. We also know that if we wanted to find the probability of someone either going to a resort or traveling or sightseeing, we would see 26% and then 17%, so we would just add those 2 values together and get 43%. Nothing too crazy there, and the fact that there's not really overlapping data makes this diagram easier to see. It's just something I wanted you to be aware of. All right, we finished this slide with a quick definition. The two events are independent if the current occurrence of one has no effect on the occurrence of other. So if two events are independent, the probability that both will occur is the probability of A times the probability of B. That's a weird multiplication symbol, but there it is. So looking at number 9, it says a random number generator on a computer selects three integers from 1 to 20. What is the probability that all three numbers are less than or equal to, that's the key, 5. All right, so less than or equal to 5 would be the numbers 1, 2, 3, 4, and 5. So that's 5 out of 20. If I were to just look simply at the first random number that's picked, we'd say we have a 5 out of 20 probability, and we would get the same probability for the second number and for the third. And when we simplify this, we get 1/64. So what is the probability of 5 randomly chosen 18 to 29-year-olds all being Twitter users? Well, what we would do in this case is just take the probabilities of each one. So if we have 1, it's 18%. I'll just write it in decimal form, 0.18. And then we're going to multiply it 5 times. So effectively what we've got here is 0.18 to the 5th power. And let's see, punching that in on the calculator, we get 3 zeros, then a 1, 8, and 9. If you wanted to write it as a percentage, it would be 0.0189%. That's what is the probability of winning. So in each game, players select 5 numbers from a set of 59 white balls. So we're going to look at these two events as separate. The first one is our complete set would look like this. It's 1 over 59C5 because we're choosing 5 of the 59. And then our second part of this is the Powerball where we have 35 balls and we're just choosing 1. So we do 1 over 35C1. So again, choosing 1 out of 35 here, 5 out of 59 here, and I've put those in the denominator because there's only one winning combination as we're defining it, getting all 6 numbers exactly the same. This is a fairly large denominator, 175,223,510. So if you want to buy 175 million tickets, you would cover every possible number combination, and you might win, although you might share it and your taxes. And yeah, it's a bad idea. Don't do it, even if you have 175 million to waste. That's another topic, though. All right. Finally, probability of a complement. Sometimes finding probabilities is a little bit challenging using the direct pathway. But if we switch it around and find the probability that the event does not occur, we can actually work on it a little bit in a little bit simpler way. So on number 12, we're going to look at that. An iPad manufacturer has found that they have 2 faulty iPads for every 5,000 they produce. The school district orders 150 of them for the junior hires to use. What's the probability that at least one of the iPads will be faulty? Now that's assuming that the 2 faulty out of 5,000 is accurate. Instead of finding out the probability of faulty, we're going to find the probability that none of them are faulty, and then we'll switch it. So we're going to do 4998 out of 5,000 to the 150th power. What this represents is the probability of 1 being not faulty, a perfect iPad, to the 150th power because we have 150 devices, and that gives us about 0.942. So what we've got going on here is the complement of what we're looking for. The probability that all of them are perfect is about 94%. So if we want to find the actual probability that at least one is broken, we would do 1 minus 0.942, and we would get 0.058 or about 5.8%. It's not that it's impossible to work through this problem in the forward direction to find out the probability of one being faulty. At least one, but it's a really complex problem that can be made simple by looking at the complement. So keep that possibility in mind as you work, and you guys have a spectacular